Welcome to my talk on chaotic pseudo-random number generators, a case study on replication study challenges. I will first give some motivation, then reprise some basics about number representations and chaotic pseudo-random number generators. Then I will report about the challenges that we have met when implementing chaotic pseudo-random number generators. I will report about experiments that we did to confirm those challenges. And finally, I will give some conclusions together with recommendations on additional things to report when doing numerical experiments in security. Pseudo-random number generators are used in many security protocols. Chaotic pseudo-random number generators seemed a useful alternative, at least for some time, compared to classic pseudo-random number generators that were used in security. Chaotic pseudo-random number generators are defined on the reals, and also their properties are derived from property of the real numbers. However, they are implemented with finite number representations. This has consequences and challenges for the replicability of experiments with these pseudo-random number generators, and it has also challenges for the quality of those pseudo-random number generators, which might be a reason that they have disappeared again from the agenda. We will report about those challenges and confirm them by experiments from which we derive some recommendations. Mainly, two types of number representations are used. One are floating point representations, which have been standardized by IEEE in 1985 and revised twice since then. A floating point number is comprised of three parts, S, E, and M, of 1, E, and M bits each, and it represents the number given in the formula. S is a sign bit, E is the exponent which gets biased in the representation, and M are the bits of the mantissa after the decimal point in the binary representation. This is true if the exponent is larger than 0. If the exponent is equal to 0, then instead of 1.m, we use 0.m, which allows to represent 0 and the so-called denormalized numbers, which are the numbers between 0 and the smallest normalized numbers of the above formula. The second type of number representations for non-integral numbers are fixed point representations with k fractional digits. With t bits in total, we represent the binary representation of the bit string t multiplied with 2 to the minus k. So we see that fixed point representations can work mainly as integers are done. The only thing is if we multiply two fixed point representations, then we need to do a k-bit shift afterwards to validate one of the two minus k. When we are doing multiplications with either number representation, the result can have more bits then can be represented. Then a rounding must occur. And here, 3 rounding modes are used. Round towards 0 always means that the superfluous bits are simply cut. Round to infinity mean if the superfluous bits are not all equal to 0, we round up. And round to nearest rounds up if the first bit to be cut off is equal to 1. A pseudo-random number generator is a generator to get bits or small numbers of bits which look like if they were random, so they fulfill some statistical tests. But all in all, this generator is deterministic. It has an inner state comprised of t bits, which is initially set by a seeding procedure. After that, until a reseeding, the generator does not receive any further input. When the generator is called, the output function O generates output which might be 1 bit or a few bits, at least fewer bits than t, from the inner state. After output has been called, the transition function is invoked and it transforms the current state into the follow-up state. An important characteristic of a pseudo-random number generator is its period, which is the number of steps that we can do before the state that had been reached in the past is reached again. If the period is too small, then we need very frequent reseedings, which complicate protocols. So the transition function f in principle can be any function, but in order to have some security properties, it should be a one-way function. And one possibility to have such function are chaotic functions. A chaotic function is a function where a small change in the input produces a large change in the output. Our example is the logistic map, which is kind of a prototype for a chaotic function. It's not one way, but still, for simplicity of presentation, we show this. It's defined on the interval between 0 and 1, and it's defined as a times x times 1 minus x. So we see that the maximum value reached is a over 4. So if a gets close to 4, the range approaches the domain, and there it exposes chaotic behavior. When we implement this function, we have several challenges, and we start with the order of evaluation. Evaluating the logistic map requires 2 multiplications, so we have 3 factors, and this means that we can have 3 different orders. On the reals, this does not matter, because the reals are commutative and associative. But multiplication on finite representation is not associative anymore due to the rounding. Now, the order of evaluation can be chosen by the implementer, by this type of coding in the source code, or even for a fixed source code, it can be chosen by the compiler during code optimization for a particular computer architecture. A second challenge that we see is the rounding mode. Here we have 3 modes that lead to different results. And although these can be chosen either by the BIOS upon switching in the computer, or by the operating system, or even by the application while it is running. Let's look at some example. Here we have A close to 4, and we have an X which is a little larger than 1/2. Now, depending on the different order of evaluation, the result differ by a relative size of 0.2%, which is notable. Even for the same execution order, for the same numeric example, choosing the 3 different rounding modes can lead to differences relative of 0.33%, which is also notable. The last challenge is the number representation used. We could either use floating point, here float or double, or fixed point, here unsigned in 32 or unsigned in 64 representations. The number representation is chosen by the implementer by coding into the source code. In most experiment descriptions that we have seen, only the representation is mentioned. But in different codes that we have seen, the evaluation order has been different. We did not see anything about the rounding mode. It seems that everyone is assuming that round to nearest is used. We have done some experiments. First experiment was to check if really all 3 rounding modes are supported and if they lead to different results. Yes, they do. The second was we checked with 63 different values of A, all very close to 4 and all very close to each other. And for each value of A and for a larger number of start values X, we looped until we found a cycle and recorded the length. So for each value of A, we recorded the maximum cycle length found, because there may be different cycles because the state graph can have different connected components. Now, over these 63 values of A, we averaged the cycle lengths, and here we see what happens when we have different rounding modes and different evaluation orders. And we see that the differences are really notable. And that the system that leads to largest cycle lengths does not necessarily lead to the best cycle lengths when looked overall. More results, for examples to minimum and maximum values, are in the paper. We come to the conclusions. We have demonstrated that tiny implementation details in a microscopically small implementation can make a difference. However, to do replication of a study, we would need all of this detailed information to be able to replicate. Thus, our recommendations are: experimenters should report the rounding mode, the number representation used, and not only floating point, but saying, are they using float or doubles? And they should mention things like evaluation order if they play a role. Moreover, in order to find out if things have an influence, implementers should check those variants, like we did, to see their influence and be able to report their influence. Our future work will be to broaden the scope from pseudo-random number generators to other numerical things in information security, do a deeper analysis, and doing more experiments. Thank you very much for your kind attention.